Okay, here we're talking about the relation between two variables. And so let's just get started. The blank, the response variable, is the variable whose value can be explained by the value of the explanatory variable. Or it's also sometimes called the predictor variable. I'm just going to abbreviate with var right there. So those are just the two variables that we're going to be dealing with, the response and the explanatory. So a scatter diagram is a graph that shows a relationship between two quantitative variables measured on the same individual. Each individual in the data set is represented by a point in the scatter diagram. The blank, the explanatory, variable is plotted on the horizontal axis, and the response variable is plotted on the vertical axis. We're going to look at an example of how to do these shortly. Alright, so that tells you where these items go. So example 1, a golf pro wants to investigate the relation between the club head speed of a golf club and the distance that the ball will travel. He realizes the other variables besides the club head speed determine the distance the ball will travel. To eliminate the variability of these variables, the pro uses a single model club, one golfer, and on a clear 70-degree day with no wind. The pro records the club head speed, measures the distance the ball travels, and collects the data in Table 1. Draw a scatter diagram of the data. Alright, so let's do that here. So we just have a chart like this, and the horizontal is our explanatory variable. The explanatory variable here is the club head speed, and we'll say club speed, and the vertical is our response. So what we're saying is this is the explanatory variable. How fast it goes will determine the response or the distance. Alright, it's important to get those two correct and understand which one is the explanatory and which one's the response. The club head speed is making the distance go, so this is responding to the club head speed. And what we do now is we just plot all of these, and we can start by saying 99, 100, 101, 102, 103, 104, 105. Alright, and then up the side we have, we're from 277 to 258. So what we'll do is we'll go up in increments of 5. We'll start at 255, 260, 270, I skipped 265, sorry, 270 here, 275, and we'll go one above the highest to 280. So what we do now is just plot these points that we're given, and you can do this in the calculator, which you'll be able to see that in the next video. So let's just start. We have 100 and 257, so roughly here. 102 and 264, so roughly here. 103 and 274, roughly here. 101, 266 is here. 105 and 277. 100, 263. 99 and 258. 105 and 275. So this is what a scatter diagram looks like. And you can see that it roughly follows a pattern. As the club head speed increases, the distance the ball travels, or the response, it travels further and further. You can kind of see that if you draw a line like this, it kind of forms a linear relationship, a linear line. And that's what we're going to be talking about today when we get the linear correlation coefficient. It measures how strong this relationship is, whether it's an increasing positive like this or if it's a decreasing negative. So we're testing linear relationships today. All right, so you can have some examples. So some examples of scatter diagrams. Here you could have, and I'm just going to roughly draw in a couple of these. You could have something like we just did here, something that has a positive relationship. This is a linear positive relationship. You could have something like this, and that would be a linear relationship also, but now that's a negative relationship. Okay, you could have something like this if you wanted. So it kind of looks like a rainbow or a parabola. Here, this would be nonlinear, so we'll just call it nonlinear for now, and we're not going to get into too much about nonlinear scatter diagrams. I just want you to see some of the possibilities. It can really be any shape that your heart desires. You could have something like this too. Just all over the place. This again is, this here is actually, you can see that there's not really a relationship at all. Everything's just kind of scattered all over the place. Here there would be no relation. But you can have basically infinite number of nonlinear. We're going to be looking at linear positive and linear negative and how strong of a linear relationship they have together. All right. So the blank, this is the linear correlation coefficient. The linear correlation coefficient. Or the Pearson product moment correlation coefficient. That's just another name for it, but we'll call it the linear correlation coefficient. Is a measure of the strength and direction of the linear relation between two quantitative variables. So that explains what we just looked at with the golf example. It's a linear relationship between two quantitative variables, and it tells us the strength and the direction. So we could clearly tell by the golf example, the graph, that it was a positive and trending up. As the club head speed increased, so did the distance. And so we're going to put that into some numbers and see how strong it is. All right. But first, the sample linear correlation coefficient. So this is just the definition, and I'm not going to make you remember this or do it by hand, but you will have to know how to do it in the calculator. In the next video, we'll show you how to do that. And you may just want to watch me. So you have this divide sign with the n minus 1 on the bottom, and then on the top is where it gets kind of funky. So you have the sum of all the x's minus the mean of x's divided by the sample standard deviation of x, and that's multiplied by all the y samples minus y bar, or its mean, divided by the sample standard deviation of the y variable. So it's kind of hairy and big, but again, just putting it here so you at least seen it once or twice. Where x bar is the sample mean of the explanatory variable, and S sub x is the sample standard deviation of the explanatory, and y bar is the sample mean of the response, and S sub y is the sample standard deviation of the response variable, and n is the number of individuals in the sample. All right. So here's an important part here to understand the properties of the linear correlation coefficient. So number one, the linear correlation coefficient is always between -1 and 1 inclusively. That means it can be -1 and 1 and anything in between. That is R. This is, remember, our correlation coefficient is labeled as R. So anytime we're asking for the variable R, or the coefficient of R, it has to be between -1 and 1. Number two, if R is equal to 1, a positive 1, then a perfect positive linear relationship exists between two variables. If R is equal to -1, then a perfect negative linear relationship exists between those two variables. So it's very difficult to get to exactly 1 or -1, especially in the real world. But the closer, and number 4 and 5 will explain a little bit, the closer R is to +1, the stronger evidence of a positive association between those two. So as long as it's getting close to 1, then that tells us that there is a positive relationship there. It could be 0.9, 0.8, and so on. The closer R is to -1, the stronger evidence of a negative relationship between those two variables. Number 6, if R is close to 0, and this is important, then little or no evidence exists of a linear relation between the two variables. Alright, so if it's 0, if R is 0 or very close to it, that doesn't tell us anything in regards to the linear relationship between those two variables. So R close to 0 does not imply no relation, it just implies no linear relation. Alright, so for example, in this one here we have a positive linear relation. Here we have a negative linear relation. But in this one, R would be 0. So over here, R would be approximately 1, and R would be approximately -1. +1 and -1. Here, R would equal 0 because there's no linear relationship. But we don't say no relation like down here because there is a relationship there. We won't get to that. So that's what R is telling us, and we're only focusing on linear relationships. 7, the linear correlation coefficient is a unitless measure of association. So the unit of measure for X and Y plays no role in the interpretation of R. So whenever you get the value of R, it doesn't tell you anything or in terms of anything related to the two variables. So in our golf example, it wouldn't, whatever the R value is there, it wouldn't mean how the distance or the club head speed. It wouldn't have any dealing with that. 8, the correlation coefficient is not resistant. Therefore, an observation that does not follow the overall pattern of the data could affect the value of the linear correlation coefficient. So if we have an outlier that's really big or really small, it could affect our correlation coefficient R. All right, example 2. For the data shown in table 2, compute the linear correlation coefficient. A scatter diagram is shown in figure 6, which that's not true because I'm going to draw one. The dashed line on the scatter diagram represents the mean of X and Y. Alright, so here, these are going to be our X's and these are going to be our Y's. And this is just to show a really simple example here. So we have 1, 3, 5, 7. Then we'll go up the side, and I'm not going to have enough room to do this example. So we'll go 5, 10, 15, and 20. That will give me just enough room. So I'll roughly plot these: 1 and 18, 3 and 13, 3 and 9, 6 and 6, 7 and 4. All right. So by looking at this graph, you can see that there is some form of negative linear relationship there. We just need to we need to figure out what that is by finding R, the correlation coefficient. Remember, right here it says compute it. So in the next example, you'll learn how to do this in the calculator. But for now, I'm just going to give you the answer so we can have something to talk about. All right. So we have R here would be negative 0.946. So that is very close to negative 1. Since R is close to negative 1, that implies a strong negative linear relationship. All right. And the last thing we need to do when we're talking about R, so we can compute R and we can get a relatively good number, say, but of like 0.9, say here. But there's still another criteria that needs to be satisfied so that we know if this is an accurate or a good representation. And it all depends on the sample size that we're using. So here we were only dealing with 5 samples. So testing for a linear relation. So we can find R, but that doesn't tell us that there is a linear relationship. It's a first step in telling us. This will finish it off so we can confirm that there is a relationship there. So step 1, determine the absolute value of the correlation coefficient R. And I'm going to work another example in a second. So the first step is determine the absolute value of R. Step 2, find the critical value in table 2 from Appendix A for the given sample size. And I have a table I'll show you here momentarily, which I'll just show you now. This is table 2, finding critical values. Okay, we'll come back to it. This N just represents our size of our sample that we're looking at. And 3, if the absolute value of the correlation coefficient is greater than the critical value, we say a linear relation exists between the two variables. Otherwise, no linear relation exists. So example 4. Determine whether a linear relation exists between the club head speed and the distance from example 1. So we're going to go back and look at that golf example. And just to refresh, I'm not going to stay on this page for very long. This was our graph. These were our numbers. We could put these in the calculator, and the calculator will also give us a scatter diagram, and we could also calculate R from there. All right, so we said that there looks like there is a positive relationship there, positive linear relationship. All right, so step 1, it says determine if the absolute value of the correlation coefficient R. So first we need to figure out what R is, and I already did that. R is equal to 0.939 in that example. So that is very close to +1, which means that would suggest that there is a positive linear relationship there. Now we need to determine if there actually is one. All right, to finish step 1, it says determine the absolute value of the correlation coefficient. So to do that, you just say the absolute value of R, which is equal to the absolute value of 0.939, which it's already a positive, so there's nothing to do here. All right. When R is negative, that's when the absolute value is useful. But for this example, it was already there. Step 2, find the critical value in the table for the given sample size. So let's come over here and look. We have 1, 2, 3, 4, 5, 6, 7, 8 samples. So we come to this table and we want to see, we want to find sample size 8, which is here. And then we come across and you see we have levels of confidence here of alpha 0.05 and alpha 0.01. Always assume alpha 0.05 unless told otherwise. So at sample size 8, its critical value is 0.707. So for n equal 8, the critical value is 0.707. Okay, now step 3, we combine these to determine if there is a relationship here. Step 3 says if the absolute value of the correlation coefficient we found in step 1 is greater than the critical value, we say a linear relationship exists. So we can say this: since the absolute value of R, which is 0.939, is greater than 0.707, then a positive linear relationship exists. All right. If we would have found that the absolute value of our correlation coefficient was less than this number, then there would not be a relationship, a linear relationship between those two variables. And so we have to take into account the sample size when we're dealing with these things. All right, that's it for now.